Welcome to Phantastic Physics. Today we're going to look at something called the law of conservation of momentum. And this is one of the most fundamental laws of physics, and it governs a lot of things that you see in your daily life. And for this demonstration, I'm going to be using two cars that are exactly the same mass. They're both 300 grams. And I'm going to be pushing these cars along this track here. And before I start the demonstration, I just want to remind the audience out there that if you want access to these concepts that we're discussing in this video, as well as many more physics concepts, you can click on the link in the description to this video below, and you can access our full year Phantastic Physics high school curriculum, perfect for teachers, for students, homeschool teachers, and anybody who wants to brush up on their physics. Okay, so now let's get into this demonstration here. If you look at the cars, one of the sides of each car has a magnet on them. So when you push them together, they're actually going to, let me try that again. I think this one came loose. If you push them together, they're actually going to bounce off. So those magnets are the same polarity. It's going to cause the cars to repel. If I turn the cars over, you're going to see when I push them together, they actually stick this time. And so those are demonstrating the two different types of collisions that can occur. The first one that was bouncy is called an elastic collision, E-L-A-S-T-I-C. And whenever you have a collision between objects where they stick together, we call that an inelastic collision, or basically non-elastic. So there's elastic, which are bouncy collisions, and there's inelastic, which are sticky collisions. We'll be demonstrating both of those types in this demonstration. But before we do, we need to discuss what momentum actually is. So we've all heard the word momentum. What is it? Momentum is a measure of the quantity of motion that an object has. It's a way to measure how much motion something has. But what do I mean by how much motion? Well, let's use a different definition for momentum that might make a little bit more sense. We can also say that momentum is a measure of how difficult it is to stop a moving object. So for example, if you look at a train on the track and it's moving towards you, it would be a very bad idea to stand on the track and try to stop the train. And that's because the train has a lot of momentum. It's very difficult to bring to a stop. But on the other hand, if you were to see a baseball flying towards you, well, that would be very easy to bring to a stop. All you have to do is reach your hand out and catch it. And so because the baseball has less momentum, it is much easier to bring to a stop. Okay, so momentum mathematically is represented by the symbol P. So lowercase p stands for momentum. Well, why didn't we use an M for momentum? Well, it's easy because M was already taken. M actually represents mass in physics. So instead of M, we use a lowercase p. So it turns out that momentum actually depends on two quantities. It depends on the mass of the object, which, like I said, is M. And it also depends on the velocity of your object, which we're going to represent with V. So if we were to write an equation for momentum, it would simply be momentum equals mass times velocity. And that means the more mass an object has, the more momentum it has. And the more velocity an object has, or faster it's moving, the more momentum that object has. So objects in our universe with the highest amount of momentum are typically really, really massive objects that are moving very fast. And so one example would be an asteroid zipping through space at very high speeds, very large mass, moving at a very high velocity, which means it has a very high amount of momentum, which would of course be devastating for our planet if that asteroid were to collide with us. Okay, so now that we have an understanding of what momentum is, we can now look at the law of conservation of momentum. So the law of conservation of momentum is simple. It simply says that in any closed system, and by closed system, I mean a system where there's no outside interference from other objects or from other forces, which includes friction, by the way. So in any closed system, the total momentum possessed by your objects before the collision is equal to their total momentum after the collision. So let me do that again. So right before they crash, if I added up their momentums, and then I added up those momentums after the crash, the law of conservation of momentum says that they would be the same. So if I were to express that mathematically on the board here, I would say this, that my total momentum, or P total, before the crash is equal to the total momentum of these cars after the crash. And that's it. So if I looked at the instant right before they collided, and I added up their combined momentums at that instant, and then I added up those combined momentums after they collided, I would get the same number. So if I started with 100 units of momentum, this law of conservation simply says I would end with 100 units of momentum. Now, if I look at this setup here, how many objects do I have in my system? I have 2. So from your perspective, we have object 1 on the left side and object 2 on the right side. So we have the yellow car and the blue car. So I can break this down even further and say the momentum of the first object, the yellow car, plus the momentum of the second object, the blue car, before they crash is equal to their combined momentums after they crash. Total momentum before equals total momentum after. And now, during this video, I'm going to do a number of demonstrations of both elastic, which are bouncy collisions, and inelastic, sticky collisions. And I'm going to demonstrate that this principle holds true no matter how much mass, how fast they're moving, or what type of collision occurs. Okay, for our first demonstration, I'm going to take both cars with exactly the same mass. I'm going to line them up at the edge of the tracks, and I'm going to push them towards each other with equal forces, or at least my best attempt to give them equal forces. So what I want you to pay attention to is what's happening to these cars before they crash and what's happening to them after they crash. And we'll see if the law of conservation of momentum holds true. Okay, so here we go on 3, 2, 1, go. Okay, interesting. So let's break this down. Before the crash, so object 1, remember we said is our yellow car. And we also know that its momentum, or P1, is mass times velocity. Remember, momentum is mass times velocity. So I can substitute an m times a v for the yellow car's momentum. And that's what it had before the crash, right? And then if we look at the other car, which is the blue one, it had the same mass, it had the same velocity, but it was moving in the opposite direction. So that means its momentum was negative. We're going to define to the left as the negative direction. So we would say it had a negative mass times velocity. So remember, we have to add the yellow car's momentum plus the blue car's momentum before the crash. And so what do you get when you add these together? How much overall momentum did we have? Well, we have mv plus negative mv. And remember, when you add a negative, that's the same as subtracting. So we basically just have this quantity minus itself. And so overall, the momentum before this crash was actually 0. And that should make sense because we had an equal amount of momentum going in both directions, which means they add up to a total of 0 overall momentum. On the after side of the equation, what did you see? Well, if I were to show that again, sorry, one more time here. This time, the yellow car goes in the negative direction and the blue car went in the positive direction, which means if I look at the after side of the equation, here's my yellow car. It had a negative mass times velocity because it had negative momentum, and the blue car had positive momentum because it went in the positive direction. So now again, we have a negative quantity plus an equal positive quantity, which adds up to an overall momentum of, you guessed it, 0. So what does this show? Well, it proves this principle that momentum is conserved. Before the crash, there was an overall momentum of 0, and after the crash, there was still an overall momentum of 0. Momentum was neither created nor destroyed. It stayed the same. Okay, so now we're going to run a second demonstration to see how the law of conservation of momentum works if things are changed a little bit. So this time I've added a couple masses to this car, and by doing so, I've effectively doubled its mass. So the yellow car has twice as much mass as the blue car, or car 1 has double the mass of car 2. But once again, I'm going to push them towards each other, and I'm going to try to do that at equal velocities. I want you to pay special attention to what they're doing right before the collision and what they're doing right after the collision. So here we go on 3, 2, 1, go. Okay, so you probably noticed that after the collision, the blue car shoots off at a very high velocity and the yellow car moves backwards at a very slow velocity. So let's look at the before and after here. The before situation, the yellow car was moving to the right, so we know it had a positive momentum, and it has a very large mass. So I'm going to represent that as a big M. And it was moving at some velocity, which wasn't very, very large. So I'll show that as a little v. And if I look at the blue car, that's our car 2. I know I have to add its momentum up. And so it was moving in the negative direction. So we're going to say it has a negative mass times some velocity, right? And so I left that mass as a smaller number because it is the less massive car, and it was moving at an equal velocity as the yellow car, but they were just moving in opposite directions. So if you were to compare this to the last demo, can we say that these two momentums add up to 0 again? So if you look at this, it actually is clear that they don't add up to 0. So in which direction was the larger momentum overall? It was actually the direction of the yellow car. Because remember, although they both moved at the same velocity, this yellow car had much more mass. And so if you add this number plus this number, what I know is I'm going to get some kind of positive number that's greater than 0 because there's more momentum coming from this car than there is from this car. Now, if I look at the other side of the equal sign, so this is the after collision part, remember we saw these cars bounce off and this one moved much, much, much faster than that car. So looking at the yellow car again, this time the yellow car is going in the negative direction after the crash. So I would say it has a negative big mass, it's the larger mass, times a very, very tiny velocity in that direction after the crash. And then I have to add up the momentum of the blue car, which remember is like a normal mass, but it moved at a really high velocity, very, very large compared to the yellow. And so I can look at this and say, well, it's a big mass times a little velocity plus a little mass times a big velocity. Shouldn't that add up to 0 because this is negative and that's positive? Well, we know it can't add up to 0. Because if we had 0 momentum after the crash, that would mean we started with a positive number and ended up with 0, which means we destroyed some momentum. It just disappeared. And that would violate the law of conservation of momentum. So we know that whatever all of this adds up to after the crash, it has to be a positive number. It has to be overall in the rightward direction because that's how much we had before the crash. And according to the law of conservation of momentum, that's how much we have after the crash. Now, it's difficult to prove this without numbers. What you can do is actually activate the sensors that are built into these cars and weigh the masses and actually do the calculations with real numbers, and you'll find this holds up to be true. So if this was like positive 10 before the crash, you would end up with positive 10 after the crash. Okay, so let's go ahead and see what happens if this time I take the second car and leave it at rest before the crash. And I take my yellow car with extra mass added to it, and I push that yellow car towards the blue car. So here we go. Right before the crash, I want you to look at what they're doing and pay attention to what they're doing immediately after the crash. Okay, so did you notice that the yellow car speed actually reduced, so its velocity goes down after hitting the blue car, and the blue car went from being at rest to actually moving fast in the rightward direction. So I'll show that one more time. Notice the yellow car slows down and the blue car speeds up. So what do we see? So if you look at the yellow car, car 1, it's a very big mass moving at some moderate velocity in that direction before they collided. And the blue car was at rest. So how much momentum does an at-rest object have? 0. Because it's not moving. You need to have velocity to have momentum. After they collided, you can see that the yellow car continues moving to the right, but this time its velocity is much smaller. So you see a reduction in speed. So now that's the momentum of the yellow car after the crash. But what about the blue car? Well, the blue car is now moving, right? Actually at a very high velocity. So I'm going to show that as a very large V. So it went from not moving to suddenly moving pretty fast. So does this prove that momentum is conserved? Well, if I add up the yellow car plus the blue car before the crash, can you agree that it's an overall positive number? I don't see any negative momentum here. All of it is a positive number. So I know it's going to be a positive. After the crash, I see two positive quantities. Basically, nothing was moving to the left at all. So a positive plus a positive is going to give us another positive. So far it's looking like momentum was conserved. It's not like we went from positive momentum overall to 0 or from positive to negative. That would break the laws of physics. Now, let's look at this in more detail. Look what happened to the yellow car before and after the crash. Well, it's the same mass, but its velocity went down. So that means individually speaking, the yellow car's momentum actually decreased. But we know momentum can't be destroyed. So where did that yellow car's extra momentum go? It went into the blue car, because now the blue car went from 0 to having some amount of momentum. So we know that the yellow car simply didn't lose momentum entirely. It actually just transferred that momentum into the blue car, which is allowed by the law of conservation of momentum. So now what I'm going to do is run a couple of inelastic collisions. So remember, inelastic collisions are collisions where the two objects hit each other and actually stick together rather than bouncing off. So I'll start by using two equal mass cars. There's no extra mass added to either of them. I'm going to push them towards each other at the same velocity, or at least I'll try, and hope that I do it successfully. On 3, 2, 1, go. I think the blue one might have been a little faster than the yellow, so let's try it. There we go, perfect. So if you hit them with just the right velocities and they're equal, what you notice is they come to a complete stop after the crash. And I'm sure you guys may have already predicted that, but again, I want to make sure that we can tie that into the law of conservation. So what was the yellow car doing before the crash? It was moving in the rightward direction, which is positive, and it has some kind of mass multiplied by some kind of velocity. And again, the blue car was moving in the negative direction. It has the same mass and the same velocity. So if I add the blue car's momentum, I'm adding a negative momentum. And so what's the overall momentum of the two cars before the collision? Well, it's some number plus an identical negative number, which is going to give us an overall momentum of 0. Okay, well, what's their overall momentum after the crash? Well, this is easy. After the crash, they come to a complete stop in the middle, and so there's absolutely no momentum in that system whatsoever. So this is a very, very simple one, because just with the naked eye, you can see that that overall momentum was 0 before the crash and very clearly 0 after the crash. So definitely momentum was conserved. The laws of physics are still working. All right, and here's one final demonstration. Once again, we're going to use an inelastic collision, so these cars are going to stick together after the crash. This time I've added two masses to the yellow car, which is basically making it twice as massive as the blue car. So we have car 1 with double the mass of car 2. And again, I'm going to push them towards each other with equal velocities, at least to the best of my ability. And we're going to see what they do before they collide and after they collide. All right, let me erase the last one. And so we have a collision on 3, 2, 1, go. And so notice that they're both moving to the right after the crash. Let me try that one more time a little bit faster so it's more dramatic. Okay, and just so you know, I'm not trying to make this one faster, so let's do it again. And so no matter what, the overall momentum after the collision is going to be in that direction. So looking at this through the lens of momentum conservation, you can see that before the collision, the yellow car was moving in the rightward direction, so it's positive. It also has a big mass, so I'm going to show a large M here for the yellow car, and it has a pretty moderate speed. And then the blue car was moving in the negative direction, so when I add its momentum, we're going to have a negative mass times a moderate speed. And I want to be clear that this big mass is going to make these two overall numbers very different, right? So the yellow car clearly has more momentum than the blue car. So what's the overall momentum before the crash? Well, it's a big positive number minus a smaller number. It's overall going to be positive. Okay. What about after the crash? Well, what happened? Now these two masses actually stick together. So this side of the equation starts to look interesting because you have, actually, let me show the yellow car as a bigger mass here. You have a big mass for the yellow car, plus a regular size mass for the blue car, right? And remember, they're stuck together. So they act like a combined mass after the collision. And because they're stuck together, they also have a combined velocity, right? So it's two things that are sort of acting like one big thing, and they're moving at a single speed together. So what do we have here on the right? Well, we have some number that's positive multiplied by some other positive. And so the overall momentum after the collision is positive. And so we started with overall rightward momentum, and after they collided, the overall momentum continued to be to the right. So we can see here that momentum was once again conserved, and the laws of physics have not been broken even one time in this entire demonstration, which I say is a very successful day of physics. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.